Hi, my name's Huw Evans. First, I'd like to thank the hosts for persevering with this meeting in such difficult times. It has happened. I'd also like to thank them for inviting me to make this lead-off presentation in the Hive monitoring section. I'm an electronic engineer. My wife's a biologist. About 10 years ago, we co-founded a company called Avianna. For the following 10 years, we ate, slept and breathed hive monitoring as a full-time job. Historically, the evolution of beekeeping technology has been characterized by long periods of steady state, punctuated by significant developments which dramatically changed the nature of the craft. Thousands and thousands of years ago, humans would find bees in the wild and just steal their honey. Then humans figured out how to bring bees in from the wild and keep them in man-made houses or hives, clay tubes in the Middle East, straw baskets or skeps in Northern Europe where it's a lot colder and they need more protection. This practice continued relatively unchanged for almost 3,000 years until a Swiss scientist came up with a movable frame hive. For the first time, you could manipulate the colony and find out what was really going on inside. This was an observation hive which provided a lot of fundamental biological concepts mainstream beekeepers and beekeeping rely on today. What I find most fascinating is that despite making all of these discoveries using an observation hive, Hubbard was completely blind. He must have had a very strong team behind him. Recently I've been informed the real genius came from his wife. I can certainly relate to that. So now we had a much better understanding of what needed to be done, but did not have a practical way to do it. That came about 50 years later with the invention of a hive that was practical to manipulate, a smoker and a centrifugal honey extractor, which for the first time enabled honey production on a commercial scale. Then again, beekeeping technology stagnated once again for almost 100 years until the invention of electronics, which opened new doors to new opportunities for the advancement of beekeeping technology. There is so much you can tell about the state of your colony by the sound that greets you when you open the hive. So it will come as little surprise to most beekeepers to know that sound's been used as a diagnostic tool for centuries. Maybe the most famous example is Edward Farrington Woods, or that nice Mr. Woods, as the Queen of England used to call him. He was a BBC sound engineer back in the 1950s. He had a very musical ear, as you needed back in the 50s as a sound engineer. There is a phenomenon known as the cocktail party effect. It's the human being's ability to eavesdrop on a conversation in a crowded room. Even if it's not the loudest conversation in the room, we somehow have this ability to filter out surrounding sounds and home in on the conversation we're trying to listen to. Eddie Woods had a really good cocktail ear. He invented a device to let him hear sounds of interest within the hive more easily. It's a bandpass filter called the Apidictor. Its creation was delayed until the invention of the transistor. He used this device to help him with swarm prediction and monitor queen health. Almost 50 years later, Jerry Brumanschenk, our host, this year came up with not only what is possibly the first smart hive, but possibly the most impressive smart hive, or one of the most impressive smart hives that has ever existed. It was a network of 27 smart hives. Each smart hive was powered by a 486 computer, as well as the usual suspects, the hive scale, brew temperature sensors, bee counters. Also had clock-driven hourly pollen samplers for heavy metal residue analysis, air pump and carbo trap samplers, semi-volatile and volatile organics. I mean, if somebody asked me that for that today, I'd say, well, I don't know. Ring me back in 3 years' time. So it really was quite incredible for the time. Jerry did some other exciting stuff. He had both research and military funding. Here we can see a landmine detector. It's a reward-based system. It's basically a feeder that smells of landmines. You turn them on, you teach the bees to chase that smell. Then when you remotely turn off all the feeders, the bees go off and find landmines. You've got to remember this is more than 20 years ago now. I think for that reason we have to put Jerry in the Hall of Fame. I invented this concept at the Hive Monitoring Workshop back in 2018. And if anybody's earned a place in there, then it's Jerry. Another dominant character from the early years is Wayne. Wayne set up a network of weighed hives back in the 1970s. Initially they were manually weighed, but Wayne pretty much pioneered the electronic hive scale. He showed off his scale back in 2012 in the first Hive Monitoring Workshop. Wayne worked at the University of Maryland and also at NASA, and using aerial photographs and hive weights, he tracked global warming, basically. And that network is pretty much the seed that turned into what is today Bee Informed Partnership. Normally hive monitoring is applied to beehives so people know about the state of the beehive colony. But Wayne's experiment was a good demonstration of the fact that bees are actually indicator species. The aim of the study was not to inform beekeepers about the state of their colonies, more to track important changes in the environment. So our aim at Avianna was to take this technology and present it as a cool product aimed at amateur beekeepers. Here are our hive scales, novel design, available in any colour you like. The donut design made the scale more suitable for a ventilated floor hive. It allowed the bees to drop debris, it would just fall through the hole, also allowed them to ventilate better when they were hot. There is a load cell in each corner and deals slightly better with uneven weights. It's not so much that what we were doing was new, as we've seen, it was more about how this technology, or the information contained within the data, could aid bee husbandry itself. We had a pretty cool UI. It was a remote hive monitoring system. The sensor data was transmitted back to the cloud. For the first time, you could check on your bees remotely using your iPhone. And this was back in 2013. The fundamental UI remains pretty much the same today. Each monitored hive is represented by a hive icon. Each sensor has a sensor icon on each hive. We move to smart icons, where we apply a layer of interpretation. For example, one of these hives has brood, the other hive doesn't have brood, and that's signified on the brood temperature icon. We added a few gimmicks, dynamic backgrounds, which change with the time of day, with the weather forecasting. It's like a virtual apiary. Everything you need to know in one single view. We sent out a lot of useful alerts. However, my favourite one was the last one. Bees collected a lot of honey that day, which had no managerial consequence. It was just nice to know. It was at this point that I realised there was a lot more to hive monitoring than just telling us things we could have found out if we'd visited the hives. It actually allowed beekeepers to become more intimate with their bees while disturbing them less. The next few slides are a preemptive tribute to Frank Linton. If I don't include them, he always has to see them at the end. In Anya's early days, we did a lot of work on swarm prediction. So how did the swarm prediction go? Let us remind ourselves of Wood's PSD or frequency spectrum, where the y-axis is amplitude, the x-axis is frequency. He noted a disturbance around 280 Hz and associated this warbling noise with the bees making preparations to swarm. We recorded sounds from 2 hives over 30 days. Actually, we recorded sounds from a lot more hives 24/7 for many years, but let's just concentrate on this 30-day period. So here are 30 consecutive frequency spectrums taken once a day, going into the page, covering a month. On one of them, the hive that swarmed, you can clearly see a warble, and it disappeared after they swarmed. This was the first data set we ever looked at. Grab your coat, Sandra, we're going home early, I said. But when we tried to roll this across more hives, over different hive types, different geographical locations, while we could also see this in some, maybe most, but some colonies warble in a slightly different way. They also make similar sort of noises when they're superseding. While it kind of worked, the system wasn't robust enough to sell as a standalone swarm prediction product. It's hard to discuss technical innovations in amateur beekeeping without discussing the flow hive. No electronics involved. It was just a neat way of removing honey without having to remove the honey box. I say no electronics, not until I built mine a smart stand. It's a very pretty hive. I wanted to somehow incorporate scales without destroying the aesthetics, which I think I did. This is my flow hive sitting on its smart stand. There's also a microphone built into the stand. We confirmed an acoustic signature for the mating flight using this hive. So a lot of that section was dedicated to my own contributions to hive monitoring. Back in 2012 at the world's first hive monitoring workshop, there was only a small handful of us. But maybe 5-6 years ago, with the advent of cheap electronics, there was a real boom in hive monitoring products. These range from simple brood temperature measurements to sophisticated in-hive units that can tell you all sorts of things about what's going on inside the hive. There must be more than 20 scale vendors out there, more, maybe double that. Bee counters, there's cameras that point at hives. There are little apps for monitoring the bees, apps for keeping your hive inspection records, even full-blown management software for running a full-scale commercial beekeeping operation. There's all sorts of stuff. It'd be unfair to mention any without mentioning them all, and to be completely honest, I don't even know what they all are these days. But there has been a significant rise in the amount of people offering commercial solutions to beehive monitoring. Another group of stakeholders in hive monitoring and the data it provides are scientists. The observer effect applies to most of science. However, Jürgen was referring to the beehive monitoring when he made this claim. Jürgen touts as the European version of Tom Seeley. Indeed, I think they were both students of Lindauer. Furthermore, Jürgen's students run around German woodland beelining feral bees back to their nests. Jürgen's also done a lot of hive monitoring in his life, specifically for research at the University of Würzburg. This is the Mark II Hobus hive, which monitors the individual temperatures between each frame. It's got multiple cameras, humidity sensors. And this is the Mark III, probably the most sophisticated observation hive on the planet. And I think that robot on earns Jürgen a place in the Hall of Fame. I don't know if there's time for this, but Jürgen once gave me a hobosphere. I think it was invented by a guy who designed engine compartments at Audi. It has a spherical blue chamber. Needless to say, we turned it into a smart hive, integrating sensors in the frames. Indeed, connectorizing the frames so you could just pull them in and out. It also has integrated scale. And it's still alive today, but possibly what they call a Darwinian hive, in that it's been populated for 4 years now, we've only ever opened it once, and it's only ever made us a single super of honey. So to summarize the benefits for scientists, the measurements are more consistent, more reliable, although a lot of people who've used the equipment may disagree with that one, but what I mean is more objective. You can assess things more objectively, and you minimize human error with respect to confusion, which reading came from which hive and things like that. The resolution is fantastic. You can take readings every couple of minutes for weeks on end. Possibly the most important one is simultaneous data collection. The flight activity of hive can change very much from 1 hour to the next. So when you start grading one hive at the top of the line, there might be a lot of bees flying. By the time you get to the bottom of the line, a lot of those bees may have stopped foraging and come back to the hive. So the only real way to do that is to grade all the hives at the same time, which would take a lot of people. So electronics do that rather well. It's non-intrusive, which minimizes the observer effects. You can also police the beekeeper and the whole experiment remotely, check everybody's doing what they're meant to be doing. Simplifies data management. The data is collected remotely into a database. You can download that into a spreadsheet on your desktop of your computer. Data scientists tend to use APIs and Python and things like that to suck it out of the database. You also have the possibility of collecting site-specific weather data, and it's scalable. It's scalable and attractive to beekeepers. If you'd like beekeepers to be part of your experimental trial, if you can add a monitoring system that also helps them keep their bees in some way, that's attractive and helps recruit them for the trials. So, what does hive monitoring bring to a commercial beekeeper? I like that photograph. When we first started doing this, we thought about how we could help commercial beekeepers make more informed decisions, aid queen selection, but I guess it generally boiled down to knowing when nectar flows start and stop without having to be there. Here's a great example of that from New Zealand, where they collect Manuka honey. The Manuka sites are remote, so they use helicopters to transport the bees. There's no cell coverage either, so we had to develop a satellite system. When it comes to satellite systems, it's all about optimization of data efficiency. You pay per meg on a SIM contract, where with satellite you pay per byte of data. So here's the result of taking satellite scales on that helicopter on that trip. They usually remove the hives by calendar, in this case around New Year. Remote access to the weight showed them weights were still increasing. They ended up leaving them there for an extra 10 days, which resulted in a lot more Manuka honey. But while remote weight data has been helping honey producers for over a decade now, technology to enable precision pollination has only just started to gain commercial traction. I'm sure at some point today we'll hear from Jerry's team about the LiDAR and possibly other methods of in-field pollination sensing. The new kid on the block is using hive monitoring to aid the pollination of crops. Here is the system from Bee Hero monitoring sunflower pollination in Israel. So it looks like this presentation both starts and ends in Israel. This in-hive unit has 12 different sensors, but the unique part of the Bee Hero system is the sheer number of sensors they have in the field. Instead of one heavily monitored hive, one of these small sensors lives in each and every hive full time. Not only does this help beekeepers build strong colonies in advance of pollination and help monitor the bees during transportation, it enables Bee Hero to track and optimize the pollination process itself. Colony fitness is a function of each colony's ability to pollinate. We can see the natural variation from hive to hive and day to day. I first presented this at Avianna last year. Bee Hero has since moved to using dynamic alarm threshold, as sometimes it's not what the bees are doing, it's what they are doing relative to their environment that's important. So imagine you have a huge pile of bee data. What does the future hold? It better allows you to consider what is normal. How normal is a hive? With enough bee data, we can create an index of normality for various in-hive parameters. Take a parameter, say the stability of a colony's brood temperature, and you want to know how normal that is. So you can use filters to build a comparable hive in comparable conditions, which of course considerably reduces the data set, but then you can see how normal your hive is. This could help scientists running experiments who need a control, a baseline, a reference of normality. I have done this to my bees. Are they still normal? But with a big enough data set, it could also provide the treatment data, a virtual experiment. The big advantage of a virtual experiment is that you don't have to wait for humans to conduct them. Computers could be running thousands of experiments per minute as we sleep in our beds. Well, thank you for listening. I hope you enjoy the rest of the conference, and I hope we can all meet up in person maybe next year for the field demonstrations that Jerry's planning then.